Okay, let's start with a really big question, one that's been around forever. Is math something we discover, or is it something we invent? It seems like a simple question, right? But it's been debated by philosophers and scientists for centuries, and we're going to dive into it today because a brand new paper suggests this isn't just some abstract philosophical argument anymore. The answer could literally reshape physics as we know it.
See, at the heart of all this is a genuine mystery. Physicists have a great name for it: the unreasonable effectiveness of mathematics. I mean, why? Why do these abstract equations that we just dream up in our heads end up describing the entire cosmos with such unbelievable accuracy?
And this is not a new idea, not at all. Way back in 1623, Galileo put it just like this. He saw the universe as this grand book that you can only read if you speak the language of math. And that idea has been the bedrock of physics for, well, 400 years now.
To really get a handle on the problem, we first have to wade into the philosophy a bit. For thousands of years, thinkers have basically split into two major camps when it comes to the question of whether numbers themselves are even real.
So it really boils down to two big ideas. On one side, you've got Platonism. The thinking here is that numbers, shapes, all that stuff, it's real. It exists out there in some kind of perfect abstract world, and we just discover it. So we didn't invent the number 2, we found it, kind of like an explorer finding a new island. Then, on the other side, you have nominalism. This view says, nope, numbers are just useful fictions we made up. They're incredible tools for sure, but at the end of the day, they're just human inventions.
For a lot of scientists, Platonism is the really intuitive view. It just makes sense, right? Math works so well because it's describing the actual blueprint of the universe. That structure is already out there, perfect and timeless, just waiting for us to figure it out. Nominalism, on the other hand, is the more skeptical take. But if numbers aren't real, if they're just a convenient story we tell ourselves, then the nominalists have a huge problem. They have to explain why this fiction is the single most powerful tool we have for predicting what happens in the real world. And as you can imagine, neither side has an easy answer. Platonists have to deal with what's called the epistemological problem. I mean, if numbers live in some perfect, abstract world, how can our physical brains even know about them? But then, the nominalists are stuck with the application problem. Why does our made-up tool work so ridiculously well? It's been a philosophical stalemate for ages.
So for hundreds of years, this debate has pretty much stayed in the philosophy department. But what if the answer isn't just philosophical? A bombshell paper from the journal AIP Advances takes this ancient question and drops it like a bomb right into the heart of modern physics.
So here's the wild idea. What if that unreasonable effectiveness of math isn't a strength at all? What if it's actually been a limitation, blinding us and hiding deep flaws in how we understand the universe?
The authors Collies and Doe, they do not pull any punches. They flat out say that physics is in a deep conceptual crisis, and they claim that because we've been prioritizing all this elegant math, we've ended up with total confusion around the most fundamental things in science: energy, mass, and time.
And this really gets to the core of their whole argument. They're saying we've gotten so obsessed with the mathematical description of things that we've lost touch with the physical reality. It's time, they say, for a totally new language.
So what does this new language even look like? Well, it's what they call a physics-first approach. Instead of starting with abstract equations and geometry, they say we need to start by describing what we can actually see: physical processes.
Just take a look at this table. This is the core of their whole new language. They make a clean split between the cause of a process, what they call a driving potential, things like temperature or pressure, and the effect of that process, an extensive state variable, like entropy or volume. Think about it. A difference in temperature causes heat to flow, but a difference in volume doesn't really cause anything by itself. The point is, this whole framework is built on cause and effect in the real world, not just abstract numbers. The way they see it, classical mechanics got us into this mess with its famous work equals force times distance equation. They argue this one-size-fits-all approach just oversimplified everything, and it blurred the lines between different kinds of energy. It led to centuries of confusion because, hey, the math worked, even if the physics underneath it all was a total mess.
So what do they propose? Rebuilding physics from the ground up. Step 1, focus on what's actually happening physically, not just the math. Step 2, define energy based on what it does in that process. And step 3, they bring in a whole new concept called momentum work, which is just a much more precise way to talk about the energy of motion, separating it out from all the other types of energy that get jumbled up in the old model.
And if you follow this physics-first logic all the way through, well, it leads to a pretty shocking conclusion, one that forces us to revisit an equation that every single one of us thinks we know.
Yep, this one. It's probably the most famous scientific statement in all of human history. An object's total energy is just its mass times the speed of light squared. It's simple, it's elegant, and it's pure math.
But the paper argues that it's incomplete. They propose we need to add a new piece to the puzzle, E equals mc squared plus something they call potential energy, or EPOT.
Okay, and this is the truly revolutionary part. They define this potential energy as the energy of hindered motion. So think about it like a compressed spring. Its motion is totally hindered, but you know it's storing a ton of energy, right? Well, following their physics-first logic, they come to this mind-blowing conclusion. This type of energy has nothing to do with mass. I mean, if they're right, this completely shatters that simple, elegant idea of mass and energy being equivalent that we've all been taught for the last 100 years.
Okay, let's pull back for a second. We started this whole thing with a philosophical debate about math, and somehow we ended up rewriting E equals mc squared. So, what's the connection here? What does this all mean? The implication is just staggering. It means that the very beauty, the very power of our mathematical language might have been a Trojan horse. It might have been hiding fundamental flaws in our physical concepts for more than a century.
What this new research is really suggesting is that by building a language based on physical processes, on actual cause and effect, we might get a much more accurate description of reality, even if it's not as mathematically pretty.
As the authors themselves warn, when we let our precise formulas mean a bunch of different things at once, like the old concept of energy, well, the physics itself becomes imprecise. The math might look perfect, but our understanding is completely flawed.
And that brings us right back to where we started. This crisis in physics forces us to ask that ancient question all over again, but now with a whole new sense of urgency. Is math the universe's true code that we're slowly discovering, or is it our own greatest invention, a tool so powerful, so beautiful, that it's now blinding us to reality itself?